Hello there. Welcome back to this video. We are going to be looking at the feedback for the Force in Motion quiz that you did. Now, all the feedback must be done in your book, so any purple pen corrections must be done into your book. Okay. Now let's look at the first question. So question one. Again, if you got question one wrong, make sure that you look at question one and then you have that purple pen in your book. Now, what is the unit for a scalar quantity? Now, scalar quantity only has magnitude. So which one is it? So you have option. So you got few options there. Which one do you think is going to be? So which one used for measurement of a scalar quantity? So we have the first one is kilogram, we have Newton, we have kilogram meter per second, meter per second squared. Okay, scalar quantity. So we got the first one is kilograms. Kilogram is the answer. So that is the measurement of mass, and mass is a scalar. So therefore, that is the answer in this case. Okay. Now, when you're doing your purple pen corrections, this is what you're going to write. So kilogram is for mass, and mass is a scalar. Okay. We are not going to just write down the answer. All right. Now, question two. Question two. I'm just going to zoom in. So question two. The distance. So we've got distance, run, time. So what is the distance? So we know that distance is equal to speed multiplied by time. So the speed given to us is 4 multiplied by 40, and this will give us an answer of 1600 meters. Again, so this is what I need to see when you're doing your bubble pen. Alright, question 3. How far will a train travel in 2 minutes? And we've got speed again. So distance is equal to speed multiplied by time. Now, the speed is 50. Now, the time in this case, we need to convert. So 2 times 60. Okay, so this is what we need to do. So 100, and then we end up with 100. So 6, 1, 2, 3 meters. Okay, so 6,000 meters in this case. Again, so this is what you need to have when you're doing your bubble pen. Okay, so this is the working out. Question 4. Which quantity is calculated from the area under the graph? So good. So we have a speed. Let's take a look. So speed time graph area is area give us the distance travel. Okay, so distance travel. Good. And then we got on question 5. Question 5, we have the average speed of the car is this much, and which travel blah blah blah. What is so travels? So the average speed in meters. So looking for speed. Speed is equal to distance over time. Now the distance given to us, travel, is 6 kilometers. Now 6 kilometers must be converted to meters. So 6,000 meters divided by the time take is 5 minutes. Now 5 minutes must be converted into seconds, so we need to time this by 60. Okay, and we're going to get, okay, so always use your calculator. I'm going to end up with 20 seconds in this case. Okay, good. Let's move to the next one. Question 6. Question 6. Okay, the gradients of this speed time graph again. So we're going to write down speed time graph. Gradient is equal to, now the gradient will give us what? The gradient will give us, so that's change the speed. Let's change the speed with time. We're changing distance over time. Okay, so speed could be velocity as well, so that's change in speed over time. So this will give us acceleration. Okay, now the question like this, I don't like the question like this, because this here, this should be velocity. Okay, so only when we have changed velocity, then do we get acceleration. Okay, so I don't like the way the word of that question. Question 7. If speed is equal to this, then what will be the answer? This is correct. So this is indeed true. If remember, we have so we know that speed equal to distance over time. So therefore, we can have distance is equal to speed time, or we can have time is equal to distance over speed. Okay, so any one of these is correct. Any one of these can be correct. Okay, so in this case, the answer is going to be B. Okay, again, so if you're not sure, you can use the triangle. So go triangle D, speed. Okay, so if you're not sure, we have the triangles there to help you out. Good. Okay, so let's keep going. Okay, so question 8. Let's go. So question 8. The car travel at the speed, so we know the speed. At which entry would it allow its speed to be calculated in meters per second? Okay, which entry would allow its meters to be calculated in meters per second? So we need to convert this to meters per second. So the speed is 50 miles per hour. So I can write this as 50 miles per hour. So per hour, that's 1 hour. So let's convert. So 50. So we know from the question, we know that 1 mile is this much. Therefore, times this much divided by hour. So 1 hour. So we need to turn 1 hour into minutes. So times 60, 60 into seconds, and then we get this one. And then we need to use our calculator. So we need to check which one is correct. Okay, so we have this times this over 360. So the answer in this case is A. So A is the answer. So again, so this is what you need to have in your book when you're doing, if you got this question 8 wrong. Okay, now question 9, look at this graph. The graph shows the object is what? What is the object doing in this particular case? Okay, so what we have is we're going to have a quick drawing of the graph here. So what we have is we have speed, and then we have time. Okay, now it goes up, then it goes flat. Okay, now what we're going to do is we're going to label these things. So what is happening in this particular case? Okay, so this is flat. This line is flat. Okay, oops, let me draw it flat properly. Flat. There we go. Now what we know is that here it is constant acceleration because at this point we are having a change in the velocity or change in speed. Okay, and then from here to here the line is flat, so we have a constant speed or velocity, so slash velocity. Okay, so this means that acceleration is 0 at this particular point. Okay, so this is what it means. Now we need to check which option is doing this. Okay, now the option that is doing this is the only option it is C in this case. So C is the answer for this one, but you need to have the whole thing for your corrections. Okay, so the graph needs to be drawn and so on. So I'm going to delete this. Okay, question 10. Let's keep going. Question 10. Now, to measure average speed of an object between 2 points, so how do we get the average speed in this case? Okay, so between 2 points, x, y. Okay, now first of all, what we need to do is speed is equal to distance over time. So what we need to know is we need distance x and y. So we need the distance between x and y, and we need the time for x and y, and then we use the equation. Okay, so that's what we need. That's how we can work at average speed. Okay, so if we know the whole distance from x and y and the whole time it took from x and y, we can get the average speed took from x and y. Good. Okay, so 11. So 11, distance travel, the distance, what distance is travel, blah blah blah, and so on. Okay, so here we have a graph. So we have a distance. sorry, speed, time graph, and we're looking for distance, so therefore we need to say area equal to distance. Okay, so in this case the area is, so this is a triangle, so this is a triangle, they're going to be, so it's equal to, so area of a triangle, we'll do half time base time height. Half base in this case is 5, height in this case is 20, yeah, I think that's 20. Okay, and then our answer is going to be, is that 20, yeah, 20, yeah, so that's 20. Okay, so half of 20 is, okay, so we got end up with 50 meters, so the distance is 50 meters, distance 50 meters. Good. Again, so these are the steps that you need to have. Good. Question 12. Okay, question 12, we have another graph here. We have velocity time graph. Which one describe what is happening? Now, all the answers are talking about acceleration, so therefore we need to do this one here. So speed. Again, I don't like this word because all the answers are talking about acceleration. So I'm going to say velocity time graph. So the gradient equal to acceleration. Okay, so the gradient, which is the change in the y over change in x. Okay, so this would be change in y, change in x, so we got change in y, change in x, so we got, so which is final velocity take away initial velocity over time. So this is the final velocity is 10, initial velocity is 0, divided by how long it took, 5, so 10 over 5. The answer is 2 meters per second squared. Okay, so therefore we have a constant acceleration. So we have a constant acceleration because the line is because the line that we have velocity time graph line is straight. Okay, good. So again, so this is what you need to have for question 12. You can see all the steps needs to be there. Right, question 13. Question 13. An object traveling at this velocity, acceleration is uniform for this much, blah blah. Calculate the straight. So in a straight line, its speed in meters becomes this one. Okay. Acceleration uniform for 5 seconds. Okay, so this acceleration. So acceleration is equal to change in velocity over time. So you know final velocity take away initial velocity over time. Now, what do we have? So we know the acceleration is 2. The final velocity we don't know. The initial velocity we know is 3. And the time it took is 4. Okay, so we need to do this. So therefore, it's going to be 2 multiplied by 4 is equal to v minus 3. Okay, so therefore we get 8 is equal to v minus 3. Therefore we get 8 plus 3 equal to v. So therefore meters per second equal to v. Okay, so this is the working out. You can see I need to see all the working out in this case. Alright, good. Question 14. Oh, actually, I missed a question. So this here is actually, this is question 14. Okay, and then we need to do question 13 now. Question 13. Right, question 13. Which entry gives the unit for distance in the right order? Okay, so just write distance, speed, and acceleration. So distance is in meters, acceleration is in meters, second, time, speed, meters per second, acceleration meters per second squared. So based on that, the answer is B. Okay, so this is an easy question, easy mark. Okay, 15 now, because we already done 14 earlier. Now 15 we got graph. Which graph best describe motion drop from rest from a surface of a deep lake? Okay, so this is the same as terminal velocity. Okay, so instead of having the object drop from in the air from high altitude, we have the object drop from the water. So we have water here, and the object is dropped from the surface of the water, fall down. Okay, so what happened is the object at this point, okay, so the object is here. Okay, so you drop it, the object accelerates. Okay, the object accelerates. We got the weight of the object here. We've got the weight of the object the same, and then we got water resistance start to kick in. Okay, so slows down due to water drag, and then the weight, okay, in this case weight equals to water drag equal to terminal velocity. Okay, it's the same thing, so all this is water. Right, so again pick the answer which is correct from the graph. So from the graph what we have is we have this one here. So velocity time, okay, so at the start it accelerates, it goes up, and what happened, it slows down because of water resistance, so it's a curve, and then when the weight matches the water resistance, so the force matches up, become balanced, and then we plateaued. There we go, same thing. Good. 16. Right, a ball thrown vertically upwards catches when it falls. If air resistance can be ignored, so ignore air resistance. What is the acceleration at B? Okay, so here we need to draw this. Okay, B, and then Q, and then R. Okay. What is the acceleration in this case? Now, it being thrown up. Okay, now what causes it to go down? It goes up, so stops, so here stops, and then goes down. Now, question is, what causes it to go down? Okay, it goes down due to force of gravity. Okay, now we know that the acceleration due to gravity is 10. So acceleration due to gravity is 10 meters per second. Okay, good. Now acceleration is a vector, so it has direction. Okay, good. Now when we're going, so P, we're going against, so P here, we're going against gravity. So P is going to be 10 meters per second squared, but negative, because we're going to against it. Okay, now at A, what happened at A? Right, so at A, what is happening at A? At A we stopped, yeah, we've stopped, the object stopped, but the force of gravity is still there. So here it is 10 meters per second squared, and then the object falls down because fall down due to the force of gravity, and the acceleration of gravity is 10 meters per second. Okay, now the question says, what is the acceleration of the object at these different points? Now the object here, what is the stone acceleration at these different points? Okay. Now, which direction is gravity acting? Gravity is always acting downwards. It's okay. So here the object is going against gravity. Okay, so the acceleration is always down. But here, since just because we're going against gravity, you just put a minus there. So therefore we've got P, Q, R. Okay. Now the acceleration because of gravity for all of these is 10. Okay, because gravity is acting on everything on Earth, and everything is the same. Now, again, meters per second squared. Now, we need to ask ourselves which direction is gravity acting? Which direction is the force due to gravity acting? So gravity is acting down. So therefore, all that acceleration is downward. So that's why eventually it reaches stop, and then it falls back down again, because the acceleration due to gravity is always there, because it's always in acceleration due to gravity, because gravity is always there. Okay, so make sure that for this one you got everything in the right order. Okay, in the right order. Good. Okay, 16, 17, 17. Which one the forces acting on an object are balanced? Which one could be true? Okay, so if you've got an object here, let's say the forces are balanced, so this is 10, this is 10. Now two things can happen. First one, the object is at rest. That's the first thing that can happen. The second thing that can happen, the object moves at constant speed. Okay, now you need to pick which one is correct in this particular case. So these are the two things that can happen when the forces are balanced. Balanced. Okay, good. 18. Question 18. The forces are when no forces are unbalanced. Which one is not possible? Okay, now we need to be careful here. So the word used is, so first of all, let's take a look. Unbalanced. Now unbalanced, we know when the force is unbalanced is something like this. Okay, so this is unbalanced. The question says the object has no unbalanced forces on it, so therefore no unbalanced forces is equal to balance. Okay, so unbalance, no unbalance is equal to balance. Now the question is which one is, the question is asking which one is not possible. So question is not possible. Okay, now first of all we need to look at what is possible. So first of all, what is possible? So if the forces are balanced, then possible the object is at rest, possible the object move at constant speed. Now if it's not possible, we need to look, for reverse. Okay, so we look for reverse means I look for, so if the object is not at rest, so the object is moving, so the object is moving. Okay, and if it's not moving at constant speed, mean the object has to accelerate or decelerate in this case. So which one is doing these things? Okay, so which one is doing these things? Okay, so the object moves and the object accelerates. In this case, the answer is C. Again, so make sure that when you're marking your work, purpling your work for question 18, this is what you need to see. Okay, good. And then we go back to 19. Oops, I'm going too far. 19. Okay, so 19, question 19, we are here. Okay, now say we have something like a terminal velocity again. From Rest Lake, the speed was recorded until it reaches the bottom. So this one, it reaches the bottom. Okay. From rest above the lake. Okay, so here we go. So this above the lake. Okay, so this is what happened. So we've got water. So this is the bottom of the lake. So release at the bottom of the lake. So what happened? Accelerate, of course. Now hit the water. Okay, so here what happened? Decelerate. And then here, got water resistance matches up. So here, the weight equal to the force of water drag equal to terminal velocity, and then it hit the bottom, pretty much stops. Okay, so which part of the graph is showing where the forces are balanced? So this is the portion of the graph we're showing. So here we go, let's take a look. Look at the graph, time, velocity. Now the object accelerates, so it goes up straight. Now here, what happened? So instead of falling through the air continuously, it hits the surface of the water. It hits the surface of water. That's when it decelerates massively. Okay, and then the water slows down. So slows down, and then it balances. It reaches terminal velocity, and then it drops down again. Okay, so I'm going to enumerate it. So number one. So this is number one. Number two. This is number two. Number three. This is number three. Number four. That's when it stops. Number four. Okay, so in your book, these are the things that you need to have. Write it down properly, annotate it, and so on. Okay, question 20. Right, 15 more questions, and then we're done. Okay, now which one's going to be according to the second? Which one will be the proper one? Okay, so top of the cliff. Here we go. Now, same thing. If you have something on your desk, for example, and then let's say you kick it, what's going to happen? It's going to go like this. Okay, now the reason why it goes like this is because of gravity. Because it goes like this, so you push it, so you have force here, you kick it, and then after that, it's only gravity. It's only gravity, so in this case, only weight that acts downwards in this case. So it always curves up. So the answer is A in this case. Again, there's nothing to think about here. Again, so if you look at the graph, if you look at your options, there's A and D. However, it can't be D because D is too curved, and that's not the case because it goes further a little bit. It goes further because you kick it. There's force there. You force it. Okay, go further, and then gravity starts to kick in. Gravity is so when you kick it, you transfer energy to it, so it goes further, and then what happens is gravity is there, so gravity starts to pull it down. Okay, now question 221. Now something we did this loads of time before. So which one's going to the right? Okay, so which one's going to the right? So we have acceleration. So pretty much. So when we have acceleration, we must have a resultant force. Okay, so which one has a resultant force? So we need to have a resultant force. So here we go. So here, so let's say this is 10, this is 2 newtons, so therefore the resultant would be the resultant would be 8 newton to the right. So the answer in this case is D, as you can see. Okay, very easy questions. Question 21 done. 22. Now 22 again, same thing here. So this time we have uniform speed. Which one is going at the uniform speed? Okay, now uniform speed just means constant speed, and the object goes at constant speed when the forces are balanced. So when the forces are balanced in this case, so the forces are balanced when the arrows are the same length. Okay, so same length arrows are the same length. Good. 23. 23. Now all need to be large. Which list has situation has to be large? Large. Okay, wheels, bearing, shoes. Okay. Alright, friction, brakes, rope. Skis, no, don't want. Okay, so friction. Okay, so why do we need friction to be large? So we need friction pretty much to move. Okay, so friction allows us to move from one place to the next place. Okay, now let's take a look. We've got shoe sole here. So let's say you're walking. Okay, so you're walking. So let's say you're walking. Okay, now if you want to go forward, okay, there must be friction behind you. Okay, so friction. There's friction. Okay, so there's friction. So if you put your feet down, okay, that's your feet, your shoes, whatever it is, on the ground. Now let's say you want to move your feet backwards, yeah? But what happened is you feel a resistance, you feel friction, okay, against you. So that's how you move very much. Because you're pushing at the back, you're pushing, and there's friction holding you into the ground. That allows you to move in a way. What else do we have? Bicycle brakes. So bicycle brakes. So you got the wheels. Okay, so you got the wheels. Then you got the brakes. Okay, so you got the brakes. The brakes are pressing on the wheels. So you need to press. So that's friction because you're in contact. You're preventing its friction. You know, it allows you to move. It also allows stop you from moving as well. Ropes. So tug of war. Ropes. So you got the ropes. So someone's holding on the ropes. Okay, so you're pulling here. Yeah, you're pulling, but there's friction. Isn't the friction in your hands? Isn't it's the friction the other way? The friction the other way. So friction is very much. It allows you to move. It's also in a way it's like a resistance. Resistive. It's a resistive force. It's a resistive force. Now wheel bearings. So in bearings wanted to move. Yeah. So bearings wanted to move. So you don't want friction to be large in bearings, but shoe soles. So soles for what? It's for friction, isn't it? So it's to prevent you from sliding. Okay, in a way, stop sliding. Here we go. Receive force, stop sliding. Good, that's easy. So the answer in this case is B. Okay, 24, 23. Okay, 24 now. 24. 24. If a car stops, suddenly stop. In a crash, white passengers who are not wearing belt move forward. Okay, so good. So let's take a look. So we've got wall. Okay. Okay, so why? So let's see. So why is the person going forward? So crash. Why is it going forward? In case this is Newton first law. Newton first law. Yeah. Okay. Since the car is in motion, so is the person inside. Okay. Now. Okay. So if car stops suddenly, Okay, so due to Newton's first law, so Newton first law, a person was already in motion, okay, stays in motion. So the person is thrown forward. Okay, now remember Newton's first law says an object at rest will stay at rest unless there's a resultant force on it. Also said an object in motion will stay in motion unless there's a resultant force on it. So in this case, only the car has come to stop, but the person, there's no force on the person. So this person will continue in motion and be front forward unless there's a resultant force. In this case, if it hits the front of the car, that's where the resultant force is going to be. Okay, so good. 24, 25. Okay, so nearly there. 25, 24. An unbalance acts on this, blah, blah, blah. The motion is what? Okay, now the motion is 1. So let's take a look. We have the force. Go to MA. So what is the motion? Motion upon acceleration. So A, go to F over M. So result unbalanced force. So we know the 20 divided by 4, 5 meters per second squared. Good. 26. So the object accelerates in this case. 26. Newton's second law can be expressed as this. Which one is correct? So we know this one here. So F is equal to MA. So we know that A is equal to F over M. M is equal to F over A. If you're not sure about the triangle, then we've got F, M, A. Here we go. Okay, good. 27, 27, 27. What's the mass? So again, so F is equal to MA. We're looking for mass. So force for A. Now the force, do we know the force? We know the force is 12. We know the acceleration is 3. And then the answer is 4 meters, so 4 kilogram, because that's the mass. 28. Question 28. So the mass accelerated this, okay? When the force is F, the acceleration would be double the mass, and by factor double the force. Alright. So let's take a look. So F equal to MA. Okay. Now, if a certain object with force M, so again we don't know the force M, so let's say it is M, the acceleration is 8. Okay, so therefore we got force equal to, when the acceleration is 8, to be 8 M here. Okay, so when the mass is M, 8, so therefore we get this one here. Okay, now what would the acceleration of double the mass be under the action of double the force? Okay, so the question is asking what would be the acceleration. Alright, interesting. Okay, how can I do this? Okay, now let's do this. Okay, now first of all we'll be looking for acceleration, isn't it? So let me rearrange this. So A is equal to F of M. Okay, now question says what's going to happen to A if the force is double, yeah, and if the mass is also double. So what happened? So if A is double, if mass is double, pretty much nothing new happens, because the force is over the mass, so it's 2 divided by 2, so nothing happens. So therefore So therefore, acceleration stays at 8 meters per second squared. So nothing new happens because, okay, so F over m multiply both sides by 2, so double the force, double the mass, so it's just 2F over 2m. So this equals to just F over m. So nothing happened. Nothing happened. So stays. So acceleration stays at 8. Good. 29. Okay, so 29. 29. Spaceship. Nice one. Alright, let's take a look. So we've got the rockets. Again, so we just draw a free body diagram. Don't need to be fancy. We know the mass of the rocket. The engine is pushing. Okay, so the engine is pushing the thrust of this. Okay, cut the engines. Okay. Alright, so when it cuts the engine, so cut engine equal to no forces. There's no forces on it. Okay, so it's the same thing as being balanced. Okay, so two things going to happen. Okay, so either the object is at rest or move at constant speeds. In this case, what's going to happen is it's going to continue moving at constant speed. So move at constant. So what is the speed? The speed is constant, 4,000 meters per second. Okay, good. 30. 30 now. I need to decrease this a little bit. So 30. The object is horizontal, caused by two forces, blah blah blah. And what is the mass of the object? So again, so this is good. So F is equal to ma. So first of all, we need to work out the resultant force. So the resultant force is 12 take away 6. Let's go to ma. So 6 is equal to m. The acceleration, do we know, is 2. So 6 divided by 2 is equal to m. So therefore, we end up with 3 kg is equal to m. Mass is equal to 3 kg. Good. Next one is 31. The reaction force of the horse pulling. Now this is reaction. So this is Newton third law. Action reaction. Okay. Now we know there. So let's take a look. So the reaction to the force of the horse pulling. Okay. So we've got the horse. Okay, now the horse, what is the horse saying? The horse is, say, the horse is pulling. Okay, so the reaction of the force of the horse pulling, okay, on the cart along a rough track is what? So what is this guy doing? So the action first. The action is pulling. So horse pulls. So pulls on the cart. Now, reaction. Now, if it's pulling on the cart, what's going to happen? So if the horse is pulling on the cart, now the cart must also be pulling on the horse. That's what happened. Okay, so cart pulls on horse. Okay, so that's what happens. In this case, the answer is C. The force of the cart on the horse. Yes, so the cart pulls on the horse. Action, reaction, pair, equal and opposite. Okay. Yeah. So that's why, as the horse moves forward, okay, the horse stays attached to the cart. Okay, The reason why the cart move forward is because it stays attached to the horse. So the forces between the horse and the cart, so the force that is holding them together, are equal and opposite. Because that's why the cart does not rip the head of the horse. That's why the horse did not rip the cart apart, because the forces are equal and opposite. And of course, we place on the wheel, so this way is able to move forward. Okay, so if you're wondering why, so 24, sorry, 22, actually 22, almost there, 22, 32, my bad, 32. The reaction of the weight of an apple sitting on the table. Okay, so this one, we know this one. So we've got the apple. So the reaction of the weight, so the weight is down. Okay, so weight is down. So what is the reaction? Now, first of all, for this question, we need to look at the options. The first option, we have the force of the apple on the earth. Okay, that is the action. That is the reaction. So we got the reaction. So the first one you ask yourself is, you have the weight of the apple. The weight of the apple sitting on the table, and the reaction. The first reaction is option A, the force of the apple on the earth. So the force. So action is the weight, and the reaction is saying the force of the apple on the earth. Okay. Now, option B, the force of the apple on the table. Okay. Option C, the force of the table on the apple. Okay. Question D, the force of the earth on the apple. Now, for Newton's third law, so what we know is, we know that the forces are, okay, so we know that forces equal to equal plus opposite. Okay, equal and opposite. And we know that the forces that are in the same plane, we know it has to be of the same type. Okay, now what we have is that we have weight here. Okay, we have got the weight in this case. Now the question is the weight here, okay? The weight, and the question saying the reaction to the weight of an apple sitting on the table. So the apple is sitting on the table. Okay, now yes, we had the weight. So normally you're going to have something like this, okay? So weight, okay? We've got the earth. Okay? Alright? So normally what you have is, you have the earth. The weight is what? The earth pulling apple, and you have apple here pulling earth. Okay? Now the forces have to be equal and opposite. Alright? And in this case the force is very small, because the apple can't pull the earth. Of course, it can't pull the earth or the water. You know, it would be crazy. Yeah, because it's pulled by small forces. Okay, now if like this, it is acceptable. But the question says it is the weight of the apple sitting on the chair. Okay, let's have a look. Oops. Okay, now the way we're going to view this question is the following. So we're going to have the table. Now, so let's say we have the apple. Now let's say the apple is in the air, like this. Okay, now the weight of the apple will make the apple fall. So the apple will fall. So pretty much the apple fall. Okay, now when the apple fall, so number one, apple fall. Number two, when apple fall, the apple is gonna be in contact. Contact Okay, so now the apple is touching the table, so it's pretty much sitting on the table. Okay, now for this one, again, I don't like the way the question's been worded. So here, so what is happening now is the weight is putting the apple down. So the apple is it's being pulled down. So therefore the apple falls on the table. So therefore now the apple is sitting on the table. Okay. Now what's happening is the action. So this is the action. So the apple is falling. Okay. Now the reaction is the apple. So it's falling. Now hit the table and therefore it sits on the table. Now for it to sit on the table, there must be a force that the apple exerts on the table. Okay, so that's what happened first. So you got the weight, so you drop the apple falls, touches the table, and then there must be a force that the apple exerts on the table. And what's going to happen is then the table will also exert an equal amount of force against the apple. So this way, the forces are the same type. Okay, again, I don't like the way the question is worded. All right. So what we have is, let's say, we can word this. So weight of apple makes it fall. Okay. So hit slash touch slash sit on table. Okay. Exert. Okay, so therefore, so that's the action. Let me just write down action. So the action, the weight, blah blah blah, and then the reaction of this is force of apple on table. Okay, and then you're gonna have like a reaction to that reaction from the table. In this case, again, I don't like the way I don't like the way they've worded this question here. Okay, so 33. Which statement about mass is not true? Okay, which one is not true? First of all, let's see what is true. So mass is measured in kg, weight is measured in Newton, mass is a scalar, weight is a vector. Okay, yeah, alright, let's take a look. So which one is not true? So therefore we need something that is not true. So this is true. So which one is not true? So therefore not true is equal to option D. So option D in this case is not true. Good. And 30 the end. 34, and then let's do 35 as well. 34. The weight is this one. What is the weight again? Weight is equal to mass times gravitational field. Mass is 3 times 10, 30 Newton. Okay, question 34. 34. Okay, again, so the question here is what is the mass and weight on the planet where gravity is this one? Okay, alright. Good. Okay, now Earth. Okay. And then new planet. Okay, so we've got the mass, we've got the weight. Now, we know that the mass of the person, woman, is this much on Earth. We know it is this much on here. Now, the mass on the different planet will also be kg, so we know that the mass stays the same. Okay, now we know that the weight will be different. So how do we know if it's different? What difference is going to be? So therefore, we need to use the equation weight is equal to mass times gravitational field. Now we're looking for weight. The weight is going to be 70 kg times the gravity of the new planet, which is this one here. Okay, and the answer is going to be, here we go. Okay, so here we go. Again, the weight is different because the weight depends on the gravitational field strength of the different planets, but your mass is how much stuff you have in your body. Okay, so hopefully you got all of these into your book and you know what you went wrong. Again, there's a few questions that especially the few questions that should have been, pretty much 2 questions that should have been worded differently. Okay, otherwise everything is basic stuff. Okay, stay alive.